issue of power transfer from a generating station to consumers located far away. Traditional AC power transmissions face huge power losses and also suffer from the issue of stability and controllability. For long-distance power transmission, HVDC technology is the right choice. In HVDC, bulk amounts of AC power have to be converted to DC with the help of converting stations. After that, the DC power is transmitted to the consumers. This important task of a conversion is performed by a unique semiconductor switching device called the thyristor, more specifically by silicon-controlled rectifiers. Let's explore how a thyristor works. You may have seen different semiconductor switching devices such as diodes and transistors. Similarly, a thyristor is also a switch. All of these switching devices are made up of the well-known semiconducting material of silicon. A thyristor is made of 4 alternating layers of N and P regions. To understand why the thyristor is used, let us look at the workings of a normal transistor, a BJT. When we connect a primary power source, we observe one of the junctions of the transistor is always reverse biased. To turn on the transistor, we just connect a secondary voltage supply between the emitter and the base terminal. This will turn the transistor on. However, if we remove the secondary voltage supply, the transistor will turn off as it needs a continuous secondary voltage supply. The need for a continuous base current supply causes a huge power loss, especially during high power applications. To overcome this problem, in 1950, William Shockley proposed a very interesting power switch known as a thyristor. In thyristors, unlike with transistors, no such continuous secondary supply is needed. After the triggering, even if you remove the secondary supply, the thyristor will keep on working. To understand the workings of a thyristor properly, first we need to understand what a depletion region is and the basic workings of a diode. A pure silicon structure is shown here. Pure silicon has very low conductivity. We can increase its conductivity by injecting N-type or P-type impurities, a process known as doping. If part of the silicon is doped with P-type and the other part with N-type, we will get a PN junction, or put simply, a diode. One interesting phenomenon happens at the junction of the PN intersection, the natural migration of electrons. This will cause the P side to be slightly negatively charged and the N side slightly positively charged. In short, a depletion region where there are no free electrons or holes formed at the PN junction. The slight negative and positive charges across the depletion region will produce an electric field in between them. This electric field causes a barrier potential. Because of the barrier potential, further natural migration of electrons will not happen. This PN junction is nothing but a diode. To see how it works, let's connect a forward voltage supply to the diode with a voltage value greater than the barrier potential. You can see that the electrons will be pushed away by the negative terminal, and they will cross the PN junction. After crossing, they will occupy the holes available in the P region. Due to the attraction of the N region, these electrons will jump to the nearby holes and the flow will continue. Here, the diode is working in a forward biased condition. However, if we reverse the supply voltage, the electrons and holes will simply move away, and the diode will not work. In the P layer, holes are the majority charge carriers. However, it should be noted that there are a few electrons in the P region as well. We call them minority carriers. It is the same case with the N region. With this basic knowledge, let us learn about the workings of the thyristor. If a silicon structure wafer is doped with 4 alternate forms of P and N types, a thyristor is born. Here also, the formation of depletion regions occurs at the junctions. Whichever way you apply a voltage in a thyristor, there will be always at least one reverse biased junction. In the second case, there is only one reverse biased junction. Let's try to make a working thyristor from this configuration. In order to make the thyristor conduct, we have to break this depletion region. In thyristors, an efficient and popular method called gate triggering is used for this. Gate triggering is the process of the injection of electrons. For this, Let's connect the secondary voltage supply to the gate and cathode terminal. This secondary supply injects a lot of electrons into the P region. As this process continues, the P region becomes overflooded with the electrons. The electrons have now become majority charge carriers in this region. In short, the P region eventually becomes an N region. This new N region will cause the depletion region to automatically diminish. As the P region has become a new N region due to the gate triggering, the three regions on the bottom side collectively become a big N region. Now, the structure of a thyristor looks like a PN junction diode. As we have seen earlier, when we apply a forward bias voltage supply to the PN junction diode, it starts conducting. At this stage, even if you remove the secondary voltage supply, the thyristor will keep on working, since the injected electrons in the P region have already made it into an N region. This way, in the thyristor, the secondary supply voltage is needed only for the triggering. Now, let's see how we can turn off a thyristor. The only way to turn off a thyristor is by applying a reverse voltage across it. The most efficient way to achieve this is by the use of an LC oscillator. In an LC oscillator, an energy exchange happens between a capacitor and an inductor. You can see a fluctuating electron flow occurs in the circuit. This means the voltage in the circuit will also oscillate as shown. Assume the peak voltage of the LC circuit is more than the voltage applied across the thyristor. If we insert the thyristor circuit into this LC circuit, the thyristor will be subjected to fluctuating voltage instead of a steady voltage. In the reverse biased voltage mode, the thyristor will definitely turn off. Without the need for secondary power, thyristors help HVDC technology to save a huge amount of electric power. We hope this video gave you a good insight about the working of thyristors. Thank you.